So here, before we get into finding the derivatives of exponential functions, I wanted to kind of walk through the derivative of e to the x, because e to the x is our baseline exponential function. Base e behaves very nicely in calculus. I know this is strange because you're probably not used to working with the number e, which is about 2.71, truncated. But it is a great number for calculus, because when we work with exponentials, the derivative of exponentials, if they're not base e, are based upon base e. And when we do logarithms, which are the inverses of exponential functions, base e, or the natural log, is going to be great, as you'll see in a future video. So I'm going to do this the long way, because we don't actually have a shortcut for e to the derivative of e to the x, because this is not one where the power rule would apply. The power rule is for polynomials, where x is in the base. So power rule is the base is the variable, the exponent is a constant. Exponentials are the other way around. The base is a constant, the variable's in the exponent. So we cannot use power rule here. So I'm going to go through this the long way using the difference quotient. So I would have a generic point, e to the x, or I'm sorry, x, e to the x. And then I move h over to the right a little bit, so x plus h. Plug that into my function to get its y coordinate. Just as a little side note, e to the x plus h, using a property of exponents, is the same as e to the x times e to the h, because if you add, or if you multiply two numbers with the same base, you end up adding their exponents. I can then go ahead and set up the slope between those 2 points. So e to the x plus h minus e to the x all over x plus h minus x. But then to get the slope of the tangent, I want to move the 2 points infinitely close together. In other words, that horizontal distance between them, h, is approaching 0. I'm then going to work on simplifying this. So the limit as h approaches 0, because I haven't found the limit yet. I already said e to the x plus h is e to the x times e to the h, and minus the e to the x. And on the bottom, I just have h. Still can't do substitution. So I have the limit as h approaches 0 of e to the x, which I pull out of the numerator, e to the h minus 1 all over h. But now, e to the x, according to my limit, h is the only thing that changes. So even though I don't know what x is, it's not changing in my limit. So e to the x, in terms of the limit, is a constant multiple, and I can pull e to the x all the way out of that limit, because in the limit, only h is changing. But I still can't do substitution here, so I've simplified all I can. We haven't learned L'Hopital's rule yet, so I'm going to use a graph to help me evaluate this limit. And so I've graphed this, what's left here, and as I'm approaching 0, I can see, oh, this is approaching 1. So I have e to the x times 1. So this means that if I want the derivative of e to the x, it's still e to the x. This is big, 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 big for us. The derivative of e to the x is itself. The only other function that is true for is y equals 0, which is a horizontal line on the x-axis. That's a very boring case. It's what's known as a trivial case. But e to the x being its own derivative is a wonderful thing. Now, we still will have to watch out for chain rule on anything that's in the exponent, or if I have to do a product rule or a power rule. But when I'm doing derivative of e to the x, it's always itself. I will admit, most people just memorize derivative of e to the x is e to the x. So some examples here. if I say h is e to the 4x, well, h prime, because base is constant, numerator and the exponent is a variable, since the base is e, the derivative is itself, but then 4x is inside of that, so I need to do times the derivative of the exponent. For the next example, 3 is a constant multiple, so it's just sitting there. Then I have e to a variable power, so its derivative is itself. But then I need times the derivative of the exponent because of the chain rule. And then here, I have got a product rule because I have 7x times e to a power. So I need to do the product rule. So I have 7x, the first, times the derivative of the second. E to a variable power is itself, times the derivative of the exponent because of the chain rule. Then back to my product rule, e plus the second times the derivative of the first. And then we will get to our exponentials that are not base e in the next video.